Okay, so that's super easy. And then we create this plot. So for this plot, for the horizontal axis, it's the flow rate. Okay, so this is the technique using this Hopper technique. So for the horizontal axis, we plot the flow rate in MSCFD. And for the vertical axis, we plot this term, PWS squared minus PWF squared divided by the flow rate. Okay, so yeah, I plot and I plot these 4 points and I calculate the trend line. So if I right click and select data, okay, this one, I can remove first like this. All right. And then select data, add. All right. You can see the axis. The X, the horizontal axis is the flow rate, this one. And for the Y axis, the Y or the vertical axis is this column. So you get that one. And you can touch these dots and right click and add trend line. Wait, this one, trend line, and then display equation on chart, display R squared. And we get the R squared of 0.8273, which is quite good for our trend lining. And I just want to color it red, and it's quite thick and dashed. Want to make it quite thick like this. And I want to make this bigger. Sorry, let's say 15 because this is important. All right. Okay, so we get this linear trend, linear equation, and I make this formula as per the technique. So it's like this. So you can use PR, which means the average reservoir pressure, or you can also use PWS or static bottom hole pressure. They are actually the same. Average reservoir pressure represented by the static bottom hole pressure. They are quite the same. But for the sake of this video, I can use PWS instead, like this. All right. So PWS squared subtracted by PWF squared equals to A multiplied by flow rate plus B multiplied by flow rate squared. All right, so that's the first equation. And for the second equation, we divide the left-hand side by the flow rate, and also the right-hand side, we divide with the flow rate. So the remaining equation will be this one. Sorry. PWS squared minus PWF squared divided by the flow rate equals to A plus B multiplied by the flow rate. And this is our main equation. And we can look at this equation from this trend line result. All right. So you see here in this equation, we get value of 0.0832. And this one, the intercept, 671.56. All right. And look at this equation. So here in my second equation, A is the intercept, okay? And you can check the note. The constant A is determined by using the stabilized data point, okay? Stabilized data point. And the constant B is established from the slope of the plot of PWS squared minus PWF squared divided by flow rate versus the flow rate, which is the slope of this plot. All right, so B is the slope, and we can directly use this value, 0.0832. All right, and for the A part, the constant A is determined by using the stabilized data point. And the stabilized data point is actually this one, the flow rate of 13,000. This one, okay? This one. So yeah, we need to calculate that part first. And we can calculate that by using this step. So this one, if we copy and or maybe I make another row like this, and let's say I just copy and paste. So to calculate A, we can just put this one to the left hand side. Okay, so you get A, but we will use the flow rate from the stabilized data point. So A is this one, okay, minus B, all right, multiplied the flow rate at stabilized step, which is 13,000. Okay, so that's very easy. The constant A is 803.36. Okay, and then let's read it with me. Solving this equation for the absolute open flow or the flow rate when the PWS minus PWF, or sorry, this one, let me change it first. Okay. Okay. Solving this equation for the AOF, absolute open flow, or flow rate when the PWS squared minus PWF squared equals to PWS squared minus this one, 14.7 or 14.65 squared, because the absolute open flow or maximum flow rate will occur at flowing bottom hole pressure of 0. All right, so